Hey everyone, Mr. Larajani here. Happy Thursday to you. I think I mentioned on Monday that I would be out of the building for a couple days. I know it's not ideal, and we've talked about that plenty of times this year. And as always, I appreciate your guys' flexibility and your patience as I'm off, expanding my skill set, I guess, and learning how to do new things. I'm actually sitting in a training today with a bunch of other teachers, and I am teaching teachers about Canvas. I guess it's a little ironic or maybe coincidental that we will be using Canvas today as a class. And hopefully next year this is something that maybe I can kind of grow with a little bit and help some other teachers implement into their classrooms too. So just a little recap on the last couple of class periods. So last Friday, you would have started an assignment, wave simulations part one. There was a little bit of reading that I put together in here, a couple pictures where we learned about some differences, with the parts of a wave, frequency, amplitude, that sort of thing, some definitions that we needed to get into our journal. And then there was a PhET simulation packet assignment that went with part two. And I believe that most of us have finished this and turned that in. I have not looked at those yet in the turn-in box. So priority number one for today is if these are not finished, if you have not had a chance to look through part one, and if you have not had a chance to look at part two of the simulation and complete the PhET simulation packet, please have that be your first task for the day in my absence. And as always, if you have some questions, just kind of mark them and set those aside so we can go over those together tomorrow, Friday, when I get back. Yesterday, you guys, if you were here, would have worked in small groups, kind of simulating the process of using sonar energy to map the ocean floor or to map something. Okay, we can use a sound wave and properties of sound waves to figure out how far objects are from us. We've all made an echo before. We've all stood on the edge of a hill or a cliff or a mountain and yelled as loud as we possibly could to try to see what it sounded like when that sound wave bounced back and reflected back in our direction. That's exactly what's happening. It's no different than standing in front of a mirror and seeing light reflected back at you, and you see an image of yourself in front of a mirror. If we stand in front of a wall and we yell at that wall, people are gonna judge you and think you're a little crazy, but you're also gonna have sound waves bounce off of that wall, just like a tennis ball would bounce off that wall, and they're gonna travel in different directions depending on the angle at which they hit that wall. And so what I wanted to do today is take that a step further, the activity you guys did in class, and do a little assignment where we're going to be calculating just some basic math here, the depth of the ocean underneath a pretend little Coast Guard boat here. I've got a wonderful picture drawn. Mine's in color. Yours is going to be in black and white. Okay. And so if you'll remember, the last time we were together in class, we talked about how sound waves, okay, they travel at different speeds depending on the type of material or the matter that they're traveling through. And that makes sense because when we think about materials and matters, we're thinking about how tightly packed are those particles. Okay, the more tightly packed those particles are, the more vibrations that can take place and the faster those vibrations take place. And sound is essentially just the vibrations of something around that energy that is produced. Okay. And so we looked at this chart briefly, and we looked at how it was separated into liquids, solids, and gases, so three common states of matter, and the average speed of a sound wave in those respected materials or types of matter. And as you get into the solids, you definitely see a drastic increase in the speed of sound. Now, there are some assumptions and some variables that we have to make, and some things that we have to ignore when we look at this. Okay, one is temperature. Temperature does affect the speed of a sound wave. So if we were to look at the speed of sound in water, for example, okay, this one right here, seawater, the temperature of that water would affect the temperature or the speed of that sound wave, and the reasoning is because we know that temperature affects particle motion. The lower the temperature, the lower the potential energy, the less particle motion there is, the easier it's going to be to vibrate those. Okay? The faster that sound wave would travel. Conversely, the higher the temperature, the more particle motion that exists, the more kinetic energy exists, the looser those particles are because they're moving around, a little bit slower speed. Okay? So that's one variable that affects these things here, as does pressure. We're not really going to get into pressure too much, but those are two common ways that you can affect the speed of sound. So you got a little assignment in front of you. Front page, you've got some calculations. Back page, you've got a picture. This is how this is going to work. Okay, let's read through the background together. So sound waves can only travel through matter. That's a fact. The speed of a sound wave varies depending on a number of variables, and I just talked about that a little bit. Those variables are temperature, pressure, and the state of the matter, whether it's a liquid, solid, or a gas. So this assignment, what we're going to do is we're going to ignore pressure and temperature, pretend like they don't exist, and we are just going to use the speed of sound traveling at 1,533 meters per second, which happens to be the number from the ocean, roughly. Okay, 1,535 on this chart. We're going to go with 1,533. Okay, so for all of your calculations, you are using this number right here as your speed. Okay, so procedure. Use the formula for distance. Okay, flashback to first semester. This is in our journals, but we're using that formula right there to solve for distance, to determine how far below a boat the ocean floor is. We're going to have 9 problems to solve. We're going to plot points on a graph. We're going to connect the plotted points to create an image of the ocean floor. And then you guys are going to get creative and maybe draw me a little picture or something. Okay, important right here. It says please pay attention to the example problem, as there's an additional step that's not included in this formula. And I'll show you that here as we do this first problem together. Let's see if I can get fancy and actually draw on my screen. Okay, so you'll notice that A, B, C, D, E, F, G, all the way down to I, okay, is referencing sonar location. So basically what that is as a boat is moving across the water, okay, in different spots along the water, it's going to make a noise or a ping. I'm sure you've heard a submarine make that noise before. And when that ping is released into the water, that sound wave is spread out, okay, at a speed of 1,533 meters per second, and it continues to travel in that speed in that direction until it hits something, and then it bounces back and goes back to the boat, and the boat records how much time that takes. And so if we know how fast that wave is moving, that sound wave, and if we know how much time it takes, we can calculate the distance pretty simply. Okay, so our first problem, let's see if I can actually do this without messing it up. So we're going to take our formula, okay, distance is equal to speed times time. It's like me drawing like a kindergartner. Okay, and we're going to look for the information in this problem to help us to figure this out. So it says at sonar location A, the boat ping was heard 0.20 seconds, okay, after it was sent. How deep is the ocean floor? Okay, so our formula is going to be distance is equal to the speed of sound in water. There's that number. So 1,533 times the amount of time it took for the boat to send that signal and then to hear it again. Okay, so 1,533 times 0.20. See if I can get my calculator up here. Oops, I accidentally cleared off my information. My bad, but I think you guys have it written down or you see where I got that from. So 306.6. Okay, so 306.6 meters would be the answer to this first problem in distance, except we have one additional step. Check it out. Let's go down to our picture. What that is saying is it took 0.2 seconds for that boat to send a signal all the way to the bottom, hit something, and go all the way back. That total distance down and back was 360 or whatever I had on my calculator meters. Okay? But we don't want to know the total distance down and back. We only want to know the total distance to the ocean floor. So what we have to do, our extra step, is we have to divide all of our answers by 2. Okay? So if that helps, or if it helps you to remember, just off here to the side, write down that your extra step is to divide all of your answers by 2. Okay? So here is my original answer, 306. Sorry, I'm a little dyslexic. Okay, 306 meters down to the bottom of the ocean floor and back up to the boat. Okay, we only want to know what it was to the ocean floor, so I'm going to go divide by 2. Okay, divide my answer by 2. And it is 153.3 meters at location A to the bottom of the ocean floor. Okay, so what I would like you guys to do on your graph is you're going to go back down to your graph, and we can round that number. We can call it 153. We can estimate it at 150. I really don't care as long as it's close. Okay. Remember, with this graph, we're actually counting distance from the boat. So you'll notice that my 0 line on my graph is here. Okay, and my graph is actually counting by 10 meters. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, all the way down to 150. If I remember correctly, my answer was 153. I hope I didn't mess that up. Okay, and so here's point A. We're going to follow the line up to 153. We're going to say it's right about there, and we're going to put a dot. Okay, and what you guys are going to do is you're going to repeat that process for B, C, D, E, and F. Okay, all those problems. You're going to use the same formula. Distance is equal to speed times time. You're going to use the same speed for every problem, 1,533 meters per second. The only thing that's going to change is the time value. And then lastly, you're going to divide all of your answers by 2 because we want to know how deep the ocean floor is, not how far down and back it is to the boat. So after you get done, I'm just making this up, you're going to get all these different points on your graph. Excuse my bad drawing. Okay, so it might look something like this. Point G. Okay, let's say it looks something like that. Okay, and then you're going to go and you're going to connect the dots to map the ocean floor. And then if you want to, you can get a little creative and you can draw a little fish down here. Maybe draw some sunken treasure or a shipwreck or some plants. I don't know. Have fun with it, okay? Mostly I care that you've got the calculations down. You understand that the speed of sound is going to vary depending on the type of matter that it's in, and that we can use some of these formulas we've been talking about for the entire year to kind of build on these same concepts, okay? So partner up if you need to, if it helps. Help each other, answer questions, solve problems. You guys know where the calculators are. There's also calculators on the Chromebooks. Again, please prioritize from last Friday the simulations on the wave first. Okay. If your group is still finishing something up from yesterday with the sensor, okay, you can do that as well. And then you've got this as an option to kind of fill out the day. We will go over everything tomorrow in class, so keep track of your questions and what you need help with. Hope you guys have a wonderful day. I really appreciate everything that you do, and we'll see you guys tomorrow. Thanks.